All right, in the last setup, we were talking about logistic growth models. We had figured out how to take something that was a differential equation, turn it into a logistic growth model that was not a differential equation anymore, that was solved for p in terms of t, and we were going to use that to model with a problem. So here is an application problem. I don't want to use an infectious disease example, so let's use a problem that's got grizzly bears. If you don't like grizzly bears, make them fluffy bunnies, whatever you'd like. So I got this new park that opens. It can support no more than 100 grizzly bears. There's 10 bears in the park right now. I'm going to model the growth with this differential equation. I got dp dt equals 1 over 1,000 p times 100 minus p. So you can see that I've taken the 100 grizzly bears and I've substituted in the 100 there for the carrying capacity. I'd like to find a logistic model. Now remember we had two formulas that we were working with last time. One of them was that dp dt was k over m times p m minus p. And the other is that when we solved it, we got that the population was the carrying capacity over 1 plus AE to the negative KT. Well, these things match up. So you notice that that K over M that's on the outside here is the same thing as the 1,000 there. So let's do a little substitution, see if I can write it as K over M equals 1 over 1,000. And then if I replace that m over there with 100, right, because the carrying capacity is 100, I can multiply top and bottom here by 10, and I end up with 10k equals 1, or k equals 110. So what's going to happen is this park first opens, right? The population is very close to 0. When the population is very close to 0, this number is big, and the population is increasing rather quickly. As that population gets half full, it's moving, and then when you get to like the 97th or the 98th bear, one bear raises its hand and says, we must pause, because the population is almost at 100, and of course when it gets to 100, then the rate of change is 0 because your park is full. So let's see if we can replace some of those things that are in that population function with numbers and solve for what we're missing so we don't have to solve this differential equation from scratch. So we said the carrying capacity was 100 over 1 plus AE to the negative, I'm going to write this as 0.1 because it's an exact value. If I had something like 4/7, I would probably keep the 4/7 in there until I got towards the end so that I don't lose accuracy along the way. All right, the first thing is I want to solve for my constant of integration. Well, the constant of integration is hiding inside the problem. That's your A. So let's look at what this looks like at time 0. So at time 0, we said the population was 10, right? The park starts with 10 bears, so the population is 10 when the time is 0. So I got 100 over 1 plus A e to the 0. Well, e to the 0 is 1, right? So if that's just 1, then I end up with 100, or actually 10, equals 100 over 1 plus A. Multiply both sides by the denominator, you get 10 times 1 plus A is 100. If you divide by 10, 1 plus A is 10, which means that A is equal to 9. So that's my first step, is I figured out what that constant of integration was, and every time I get another piece, I'm going to tack it onto that problem. So now I can write it as the population is 100 over 1 plus 9e to the negative 0.1 times t. Okay, so that's actually the answer to part A. That's my logistic growth model. The second part now asks me how to figure out how long it's going to be until I've reached 50 bears. Now, you realize that 50 bears is half the carrying capacity, and that will come up with more significance in a second. So 50 bears is half the carrying capacity. All right, so let's put a 50 in for the population. 50 equals 100 over 1 plus 9e to the negative 0.1 t. If I hit both sides with that denominator, I get 50 times 1 plus 9e to the negative 0.1 t. And when I divide both sides through, I just end up with a 2 on the right-hand side. Which actually will be consistent, right? If I want to find half the carrying capacity, if the carrying capacity was 300, then I'd put 150 on the left side, and I would still end up with a 2 in that spot. All right, subtract a 1 from both sides, and I'm left with 9e to the negative 0.1 t is equal to 1. And the rest of this from here on is more pre-calc and algebra than anything else, right? Divide both sides by 9, and you'll get e to the negative 0.1 t equals 1/9. Now you need natural logs of both sides. So when you take, here we go, natural log of this side, you'll take the natural log of that side. Natural log of e to a power is just that power. So I get negative 0.1 t equals the natural log of 1/9, and divide both sides by negative 0.1, which will be okay, because remember the natural log of 1/9 is a negative number because it's less than 1. Divide that by something that's already negative, and we'll see what we got. Now, you realize when I fled my office last week, the one thing I didn't bring home was a scientific calculator. So let's take 1/9, and then we'll take the natural log of 1/9, and we'll divide it by negative 0.1, and I get 21.97 for my t. T equals 21.97. Now this is in years, so these bears are not congregating real fast. It's going to take almost 22 years until it reaches half the carrying capacity. Let's graph this and see what happens, because there's actually something interesting that comes off of this. All right, so then I can translate this over to Desmos. Let's give this a try. All right, so over here, maybe you can't see the end of this, but it is there. I'm going to punch in y equals, and then I'll put in my differential, my logistic growth function. So 100 divided by 1 plus 9e to the negative 0.1. I'm going to use x because I think that's how this system is set up. Okay, so there is my logistic growth curve. You realize we don't see anything because we're way out of the window, right? The carrying capacity is 100. So let's go up here, and I'm going to set up my x's to go from, I don't know, 0 to 50. Because if you told me it took 22 years just to get the first group in there, I'm going to go from 0 to 50 on the x's. And the y's, let's let them go from 0 to 100, because 100 is the carrying capacity, so that would make sense to use 100 as the maximum. And all of a sudden now, here, I'm going to push this aside so you can see more of the graph. There we go. All right, so there's the 10 bears that were in the park at the beginning. If I zoom this out even further, now this begins to look like a logistic growth curve. There's something interesting that happens on this logistic growth curve. And one of them is simply that I can find out the place where this thing is growing the fastest, and that's right over there, right? The carrying capacity, where it reaches half the carrying capacity, that's actually also the place where it grows the fastest. So wherever it grows the fastest, that's half the carrying capacity. The other thing that's interesting is this. That place where it's half the carrying capacity also turns out that that's the place where the graph changes concavity. So this spot over here, where we're at 21, almost 22 years, that thing there is the place where the graph changes from being concave up to being concave down. If you or quarantine long enough and you want to figure that out by actually taking my logistic growth curve and taking two derivatives, you are welcome to do that. I'm not going to do that whole thing out here, but you can see roughly that if I had a logistic growth curve to start out with 10 bears, went up, and then leveled off, wherever it reaches half of the carrying capacity, that's also the place where the graph changes concavity. So it takes about 22 years to reach half the carrying capacity. Graph it, and you'll see that you end up with a curve that's got a horizontal asymptote at 100, right? That's the carrying capacity. That's when the forest is full. All right, let's do one more application of this, and that is Newton's law of cooling. And I'd like to bring in the definition so that I don't have to type the whole thing over again. So let's see if I can bring in my definition of Newton's law of cooling here. There it is. All right. So Newton's law of cooling is again related to a difference, right? So in this case, we're talking about, let's say, a hot apple pie that you take out of the oven, right? The hot apple pie is 350 degrees, and you leave it to cool in your room temperature kitchen, which is like, what, 68, 70 degrees. When the pie is very hot, room temperature is 70, it's going to start off by cooling very quickly because the difference between the pi and the room temperature is quite a bit. As it starts getting down to 150 degrees, 100 degrees, 80 degrees, that rate at which it cools is going to start really slowing down because the difference between the room and the pi is very small. In the same way, if you took that pi and you stuck it outside and it was like 5 degrees outside, it's going to cool a whole lot faster than it is in your 70-degree kitchen. So the bigger the difference between the two temperatures, the faster that thing is going to cool. It actually works in the other direction too. If you're shoveling snow with a metal snow shovel and you bring it inside, it's going to begin to warm up very quickly at the beginning and then level off. But it's never going to get warmer than room temperature, just like your pie is never going to get cooler than the surrounding medium. So in that case, your room is the surrounding medium. So the rate of change of an object's temperature, we use capital T for temperature and lowercase t for time, is proportional to the difference between its temperature and the temperature of the surrounding medium. We usually use a little subscript there for T sub s, assuming the temperature of the surrounding medium stays fairly constant. So if you take that pizza, let's say, and you stick it in one of those delivery bags, it's not going to cool because the delivery bag is going to warm up to the temperature of the pizza, and now Newton's law of cooling no longer applies to that situation because you've changed it. On the other hand, unless you have a really, really small kitchen, that warm pie is not going to change the temperature of the kitchen that significantly that Newton's law of cooling wouldn't be valid anymore. So Newton's law of cooling, the formula looks like this. The rate of change of the temperature with respect to time is going to be the opposite of some constant, right, because it's cooling. And here's the difference between the temperature of the object and the temperature of the surrounding medium. This one is a lot easier to solve than that differential equation that we had for logistic growth before. Because here, if I separate my variables, I'll end up with a dt over t minus t sub s. And on the other side, a negative k dt. When I integrate both sides, I end up with a natural log of t minus t sub s. I'm assuming cooling in this case, so I'm not going to put my absolute values because the temperature of the object that's cooling will be warmer than, or the very worst case, equal to, the temperature of the surrounding environment. Over here, I get a negative kt, e to both sides, and I get t minus t sub s equals negative kt plus a constant, right? So I'll end up with an e to that side. And then what happens is, and we've done this before, I can break this thing apart. I'll call this a c sub 1, and then I'll remember that I can break this up into an e to the negative kt times e to some constant, and I can go back and I can rename this thing as my constant of integration. All right, so I end up with a formula that looks like this. I'm going to move that t sub s over to the other side, plus some constant times e to the negative kt. Now, your textbook is a slightly different version of this, and I'll show you what they did in a minute. But here, look at those beautiful lines that I drew around that. That is Newton's law of cooling. That the temperature of the object is the temperature of the surrounding medium plus some constant times e to the negative kt, and we'll figure out what those constants are as we go along. All right, are you ready for an example? Right, I have an example of Newton's law of cooling all ready to go. So let's take it. I'll put it in a text box for you. And this is my hard-boiled example that I'm going to use for Newton's law of cooling. So as a hard-boiled egg is 98 degrees centigrade, is put in a pan under running water. That running water is so that the temperature of the surrounding medium stays fairly constant. So it's running water, 18 degrees centigrade, and it's going to cool. After 5 minutes, the egg's temperature is 38 degrees. How much longer being a key word here, will it take to reach 20 degrees centigrade? So we start off with our formula. Right? Our temperature of the object is the temperature of the surrounding medium plus some constant times e to the negative kt. Well, let's first start off with this. The temperature of the object is 98 degrees when the temperature of the surrounding medium is 18 degrees and time is 0. So I get 98 equals 18 plus some constant times e to the 0. Well, that e to the 0 is 1, right? So you realize that the constant of integration is actually the difference between the temperature of the object and the temperature of the surrounding medium. So in this case, it's 80. And I think your textbook has a formula where they actually combine the two of them together so that it creates a difference between the temperature of the object and the temperature of the surrounding medium as the constant of integration. So they may have just filled that directly into the formula there. Either way, it's the same thing. All right, so let's now fill in what we know. The temperature of the object is going to be 18 plus 80 e to the negative kt. Now, another piece of information. After 5 minutes, then the egg's temperature is 38 degrees. Temperature of the surrounding medium is still the same. All right, so 38 equals 18 plus 80e to the negative 5k. All right, bring things over and divide. 38 minus 18 is 20. And we're going to divide both sides by 80. Can I do that in one shot just to save some space? All right, I'm going to move along here. 20 divided by 80 is exactly a quarter. So I will turn it into a decimal only because it's an exact value. Otherwise, I would carry down either a lot of decimal places or an exact value. All right, looks like we're going to have to take natural logs of both sides. So take natural log of a quarter. Natural log of e to a power is just that power. Divide both sides by negative 5. So like I said, I'm playing with my cell phone calculator because my real calculator is sitting in my office and apparently is quarantined at this point. So let's take the natural log of a quarter and then we'll divide it by negative 5. So keeping as many decimal places, let's try for, I don't know, this will give me 0.277259, right? Because that 8 rounds up to a 9. So that's my K. All right, let's take that, throw it into my formula. The temperature of the object is going to be 18 plus 80 e to the negative 0.277259 t. And now the question was, how much longer is it going to take until it reaches 20 degrees Celsius? Well, 20 degrees Celsius means we put the 20 in for t and then solve for the little t. So we're almost there. If I put a 20 in there, I'm going to subtract 18 from both sides and divide by 80. Okay. Natural logs of both sides, so 20 divided by 20 minus 18 is 2. 2 over 80 is a 40th. So I get the natural log of 1 over 40 equals negative 0.277259 t. Divide both sides by that coefficient. And we'll come up with a number, right? We'll come up with 13.305. But that's not my final answer, because if I scroll way up here, the question said, how much longer will it take? Well, how much longer will it take? It's already been going for 5 minutes. So if 13.305 is the total, take 13.305, subtract the 5 minutes that it's already been in there, and it will take 8.305 minutes more for that egg to cool down. So maybe I want to find out how long it is until I can handle it or how long it is until it's comfortable to eat. In this case, it's going to be another 8 minutes. Now, you notice that it cooled off pretty quickly at the beginning. It went down from 98 degrees to 38 degrees. So it dropped 60 degrees in those first 5 minutes. And now, to drop the next 18 degrees takes another 8 minutes. So it begins cooling much more slowly as it moves on. So at the beginning, the rate of change is very quickly for this egg. No yolk. But as it goes further along, then it takes much more time. All right? That's my example for Newton's law of cooling.